Dear first grade students at the Faculty of Commerce at Banha University in both Banha campus and Abur campus, welcome to the recorded lecture series for the module entitled Economics of Natural Resources and Environment. Recorded lectures are used in conjunction with face-to-face interactive lectures in the hybrid educational system at our university. The lecture is divided to two equal halves. One half is delivered on campus, whereas the other half is delivered via a recorded lecture. Recorded lectures are to be used in conjunction with your course textbooks. The current course is designed to be accessible to students who have not completed any introductory course in economics. The main source of the current presentation is Chapter 20 of Harris and Roach 2018. The title of the chapter is Water Economics and Policy. This chapter addresses many issues including the extent of global water scarcity, shortage of water, and whether water markets can promote more efficient water use. Moreover, the chapter highlights the question of whether water is a private good or a common property resource. The main point to be analyzed during the current lecture is global supply and demand for water. This point will be discussed through covering many points that include the hydrologic cycle and the composition of the planet's water. Moreover, we will discuss other relating issues that include the potential for water scarcity, water demand and water footprint, and the future of water over the horizon 2050. By the end of the current lecture, the student should be able to define and distinguish among basic hydrologic terminologies such as surface water, groundwater, aquifers, etc. Moreover, students should be aware of the issue of potential scarcity of water. They should be able to differentiate between the different levels of water scarcity, which are water stressed, water scarce, and absolute water scarcity. Furthermore, the student will be able to analyze the full impact of human activity on water resources, that is to say, virtual water. Thus, the student can identify countries that are net importers of virtual water and those which are not exporters of virtual water. Water is a unique natural resource that forms the basis for life on our planet. Water could be classified under two main types: that are salt water and fresh water. Salt water, such as oceans and inland seas, represents 97% of the Earth's water. Fresh water, such as rivers and groundwater, accounts for only 3% of the Earth's water. With regard to fresh water, 70% of it is in solid form, captured by the polar ice caps and by glaciers, as shown in the attached figure. In addition, the attached figure tells us that 30% of fresh water is available in its liquid form. Liquid fresh water includes both surface fresh water, such as rivers, and groundwater. Groundwater represents 29% of fresh water on Earth. The surface fresh water, such as rivers and lakes, represents only 1% of the planet's fresh water. Now, let's define and distinguish among basic hydrologic terminologies such as surface water, groundwater, and aquifers. Surface water is a renewable resource. It consists of the fresh water in rivers, lakes, and reservoirs that collects and flow on the Earth's surface. In addition, surface water includes salt water in oceans and in inland seas. Surface water covers 70% of our planet. In contrast to surface water, groundwater collects in porous layers of underground rock known as aquifers. In other words, aquifer could be defined as a layer of rock or soil that can absorb and hold water. Some groundwater is renewed by percolation of rain or melted snow. Most of groundwater was accumulated over geologic time. Some aquifers are non-recharging because of their location. Thus, they are non-renewable resources. I mean that these aquifers cannot be recharged once they are depleted. The renewable supply of water on our planet is governed by the hydrologic cycle. Hydrologic cycle is the natural purification of water through evaporation and precipitation. Thus, we could say that a hydrologic cycle is a system of continuous water circulation as shown in the attached figure. Each year, enormous quantities of water evaporates into the atmosphere from lakes, rivers, oceans, etc. Then water returns to the surface of the earth as precipitation that replenishes freshwater sources. Although surface freshwater can be considered as renewable resource, it is still available in limited supply. The flows of freshwater that are recycled in the hydrologic cycles can become stocks in two types of natural reservoirs: bodies of surface water such as lakes and rivers, and stocks of groundwater which are found in aquifers. Aquifers are replenished as a result of surface water infiltration. Most aquifers have very long replenishment times, making them essentially non-renewable resources on a human time scale. For example, aquifers under the Sahara are thousands of years old and are sometimes referred to as fossil water. On a global scale, the amount of available water exceeds the demand for it, but at particular times and in many locations, water scarcity is already a serious problem. In many parts of the world, excess demand for water is causing great stress. Groundwater levels have also been declining in many areas due to intensive pumping. In a number of places, including Africa and China, current use of water exceeds replenishable supplies, implying that aquifers are being irreversibly drained. Water is a life-sustaining replenishable resource, meaning that although stocks do not grow over time, some can be replenished within a reasonable length of time. The total global water supply is sufficient to meet human needs. However, not all water can be captured for human use. Around 2/3 of the total water supply runs off as floods. Some water must also be allocated to meet ecological demands, such as supplying wetlands and wildlife habitat. Most important, water is not evenly distributed geographically and seasonally. Some regions of the world have abundant water resources. In contrast, other regions suffer from a scarcity of water. Countries could be classified under three groups according to water scarcity. In a water-stressed country, the country has an available water supply between 1,000 and 1,700 cubic meters per person per year. If water supplies are below 1,000 cubic meters per person per year, then the country is classified as water scarce, causing a severe constraint in food production, economic development, and protection of natural systems. Finally, a country faces a situation of absolute water scarcity when freshwater supplies drop below 500 cubic meters per person per year. Table 20.1 shows freshwater availability in major regions of the world. The Middle East and North African region already experiences a situation of absolute water scarcity. Sub-Saharan Africa suffers from water scarcity. In contrast, a person in other regions has abundant supply of fresh water each year. For example, in Europe and North America, a person has a supply of fresh water above 7,000 cubic meters per year. Let's consider the uses of water in modern societies from a global perspective. We could use figure number 20.4 in this regard. Water demand can be measured in a number of ways. The simplest way is the amount of total freshwater withdrawals for various sectors of the economy. According to figure 2.4, agriculture is the largest water consuming sector. Although 80% of the world's cropland is rain-fed, the 20% that requires irrigation produces 40% of the world's food supply. The water needed for irrigated agriculture amounted to 70% of global water withdrawals. Another 20% of global water withdrawals is for industrial demands, including electricity generation. Only 10% of water is used to meet municipal and domestic demands. These percentages are global averages, but they vary significantly from country to country. In the developing world, freshwater withdrawals are often mostly used for agriculture. For example, agriculture accounts for 86% of water withdrawals in Egypt. To analyze the full impact of human activity on water resources, scientists have proposed the concept of virtual water. Virtual water could be defined as the water used throughout the production process for a particular good or service. Agriculture goods need water to grow plants and to raise cattle and other livestock. Industrial goods require water as raw material or as part of the production process. Both agricultural and industrial sectors also consume water indirectly through their demand for energy. The energy sector uses water at all stages of energy extraction, production, and consumption. Conventional natural gas is the least water-intensive fuel, using only 1/5 as much water as conventional oil. Biofuels produced from irrigated fields of corn require 3,000 times more water than conventional oil. Table 20.2 presents the amount of virtual water embedded in some common goods. For example, to produce one burger, we need to use 2,400 liters of water. Moreover, we need to use 40 liters of water to produce one slice of bread and 13 liters of water to produce one tomato. Now, could you imagine the quantity of water embedded in a burger sandwich? Measures of virtual water can be used to develop the concept of a water footprint. The water footprint could be defined as the total amount of water consumed by a human entity, whether individual, family, city, corporation, or country, whether directly or indirectly. Water footprint is calculated by summing all the virtual water embedded in the products, energy, and services used by this entity. Thus, we could say that water footprint is an indicator of total impact on freshwater resources, including both direct and indirect uses of water. The water footprint of the average person on the planet is 1,056 gallons of water per day. That is enough to fill up 21 standard bathtubs. The average water footprint of an American citizen is more than twice the global average. Figure 20.5 presents water footprints for a selection of countries. In this figure, water footprints are calculated in cubic meters per person per year. As seen in this figure, the water footprint of people in lower income countries is significantly less than the US footprint. Water footprints take into account all the water embedded in the goods and services consumed in a country, regardless of whether this water comes from the national resources inside the borders of the country or whether it comes from other parts of the world. Hence, there is an invisible circulation of water takes place between countries through trade. We could say that water-scarce countries can consume imported products that would have been too water-consuming to produce within their own water resources. But it seems that trade does not necessarily follow a logical pattern in terms of water transfer. Let's consider some examples. The cotton industry, for instance, is particularly water intensive. A single cotton t-shirt contains 2,700 liters of virtual water. Cotton is often produced in water-stressed or water-scarce countries such as India, Pakistan, or Egypt. The water footprint of the exports of cotton from India to Europe represents more than 5 billion cubic meters of water per year, while 2/3 of the population of India lacks access to improved sanitation. Moreover, 77 million of Indian people lacks access to safe water. On the other hand, European countries, which are far from being water scarce, have living styles that require massive imports of water-intensive goods. As a result, 40% of Europe's water footprint lies outside of its borders. In the case of Germany, around 69% of water footprint lies outside its borders. Figure 20.6 shows a map of the world identifying countries which are net importers of virtual water and countries which are net exporters of virtual water. Regions which are net importers of virtual water have varying shades of gray. Net importers of virtual water include many African countries that are experiencing water stress. Regions classified as net exporters of virtual water, such as North America and Australia, have varying shades of blue. These net exporters of virtual water are water abundant. It is worth mentioning that many of the Asian countries that are experiencing water stress are virtual water exporters, including India, Pakistan, and China. On the other hand, countries that are relatively water abundant, such as Italy or Japan, are virtual water importers. Global demand for water is expected to increase by 55% in 2050 compared with 2000, as shown in figure 20.7. All the demand growth is expected to occur in developing countries, mainly in China and India. The global demand for irrigation water is actually predicted to decline in the coming decades. This is due to increased irrigation efficiency, in contrast, significant increase in demand for water is expected for manufacturing, domestic, and electricity needs. One piece of good news is that access to safe drinking water supplies is expanding in developing countries. Expanding access to safe drinking water is one of the Millennium Development Goals set by the United Nations. However, progress in expanding access to safe water has been uneven. About half the progress occurred in China and India, while in some African countries, safe water access has declined since 1990. The next slide displays key concepts and terms which have been introduced during the current lecture. Kindly spend enough time in studying these concepts and terms. This is the end of today's recorded lecture. Thank you.